Welcome to the digital communication session. Now in today's session we will do the digital modulation schemes BPSK and BFSK. Now BPSK is binary phase shift key and BFSK is binary frequency shift key. Now so far we have done ASK, that is amplitude shift key, in which we will vary the amplitude with respect to modulating signal. Amplitude of the carrier will vary with respect to digital modulating signal. Now in BPSK, the phase of the carrier vary with respect to digital modulating signal, and BFSK frequency of the carrier vary with respect to digital modulating signal. Now phase shift key. Now here the B stand for binary, that is having 2 bits, either 0 or 1. So we will vary the phase of the carrier with respect to this bits 0 or 1. The phase of the carrier, like this is our carrier signal, the phase of the carrier will vary with respect to 0 or 1. Now if we are having a 0 bit, there is a phase change. If you are having a 1 bit, there is a no phase change. Now the equation of carrier signal A cos 2 pi FCT plus phi. Now for the 1 bit, the phi will be 0. For the 0 bit, the phi will be 180 degree phase shift. Here for the binary PSK, phase states of 0 degree or 180 degree. 0 degree for 1 bit and for 180 degree for 0 bit. These are the different type of modulation schemes for as compared to ASK. In this PSK, you can see the phase of the carrier is vary. At this point, you can see here there is a phase change. Instead of going down, it will going from the upper side. Now again, whenever the bit will change, here you can see 1 and 0. Here is the phase change is here taking place. At this point, another phase shift change is taking place. With PSK, the information contained in the instantaneous phase of the modulated carrier. The equation of this phase will be vary with respect to modulating signal. Now see here the picture diagram of PSK. Suppose our data is 1 0 1 0. First of all, we have to do the line coding for this signal. So we will use polar NRZ. 1 will be represented as a +1 and 0 will be represented as a -1. Again +1 and -1 is the +1 volt, -1 volt. Now BPSK, binary phase shift key, is our binary data modulating signal, digital signal. 1 will be represented as a plus voltage, 0 will be represented as a minus voltage. Like now carrier signal, this is carrier signal A cos 2 pi FCT. Now phase will vary with respect to 0 bit or 1 bit. 1 bit is there, then equation is of the carrier is A cos 2 pi FCT plus 0, that is A cos 2 pi FCT. When the 0 bit is there, equation is A cos 2 pi FCT plus का 180 degree. There is a phase change, that will be equal to minus का A cos 2 pi FCT. 180 degree can be as a pi. So A cos 2 pi FCT plus का pi, that will give to minus A cos 2 pi FCT. The net equation of the PSK is become plus minus A cos 2 pi FCT. Now plus for the 1 bit and minus for the 0 bit. Now here we are mixing these two signals to generating this PSK waveform plus minus A cos 2 pi FCT, plus stand for 1 bit and 0 stand for minus bit. Now the waveform of the PSK, here you can see at this point and this point phase will be the change. Now at this point you can see at this point phase is changing because of the transition of the 1 to 0, 0 to 1. At this point, 2 point, 3 point, you can see one phase shift is there, one phase shift is there, one phase shift is there. This is the PSK, binary PSK. Now next is the block diagram of PSK. Now in the block diagram of PSK, first we have the binary data, then we are converting this binary data into unipolar to bipolar NRZ that will generate over 0 as a minus 1 volt and 1 as a plus 1 volt. Now this will be multiplied by this product modulator and carrier will be given in this modulator, and here we are getting the PSK waveform. This is the block diagram of PSK. Binary data, unipolar to bipolar NRZ, product modulator, carrier will be, properties of the carrier will be vary, means the phase will be vary with respect to this signal, the incoming this signal, and you are getting the PSK waveform. Now next part is our bandwidth. Bandwidth of PSK. Now as we have done for the ASK, same is step for the PSK. Now our modulating signal, one will be presented as a plus 1 volt. The duration of the bit is TB, and we take the Fourier transform of this. It will give you 1 by TB minus 1 by TB is the Fourier transform. This is sending by the carrier pulse, so it will be move along the carrier pulse. The Fourier transform of PSK waveform will be like this. This is the carrier, FC plus ka 1 upon TB and FC minus ka 1 upon TB. The bandwidth will be the difference between these two. Then bandwidth is FC plus 1 upon TB minus FC plus 1 upon TB, that will give you 2 TB, that is 2 FB, that is 2 RB. Bandwidth of the PSK is same as of the ASK, 2 FB and it is 2 RB. So bandwidth of PSK is same as of ASK. Now next is our after bandwidth energy space diagram, or you can say constellation diagram. Or you can say constellation diagram. Now energy space diagram, that is help us to find out the probability of error, that will give you the Euclidean distance between the two symbols. Here we are transmitting two symbols, that is symbol 1 and symbol 0. Now for the symbol 1 equation is A cos 2 pi FCT and minus A cos 2 pi FCT, right? A and minus A. Now in terms of energy, we have to write the equation in terms of energy, that will be EB 2 by TB cos 2 pi FCT and root EB minus 2 by TB cos 2 pi FCT. Now these are the two equations in terms of energy. EB cos 2 pi FCT plus EB minus EB for 0 bit and 1 bit. Now we have to draw the energy space diagram. We will consider these two as a orthogonal function that should be normalized to 1. Orthogonal function, normalized value should be 1. So in terms of energy, we have to find out the Euclidean distance between the symbol 1 and 0. So we are plotting it. If you are taking this as a 2 by TB cos 2 pi FCT and this is as a minus 2 by TB cos 2 pi FCT. Now distance for the symbol 1, that is root EB along this having a distance that is root EB. Now for symbol 0, it having a minus root EB, for minus is here cos 2 pi FCT orthogonal function, that is here minus root EB. Now we have to find out the distance between these two. So distance between these two is this part and this part. So distance will be come out root EB minus root EB, that will give you 2 root EB. So this is the distance of Euclidean distance of symbol 0 and 1 for the PSK. For the ASK, we have calculated the distance, that is root EB. As you can see, distance is increase here. So then probability of error is inversely proportional to the distance. So as the distance is increases, probability of error will be decreased. The probability of error should be minimum when we increase the distance, right? So as compared to ASK, PSK having the less probability of error because of the high distance, that is 2 root EB. Next is our next is our reception of PSK demodulation. Now demodulation of PSK is little bit difficult because we have to perfectly match the phase of the carrier. For demodulation of PSK, we will use the coherent detection method. What is the coherent? Coherent means we are using the same carrier that we have used at the transmitter end. So maintaining that phase, because the phase of the PSK is vary with respect to modulating signals, so we have to perfectly match that phase with the that we have used in the transmitter end. Here we will use the PSK. First, it will pass to the square law device, then band pass filter, then frequency divider, product modulator, and then LPF, voltage comparator, and then symbol 1 or symbol 0. Now this is the reception of the demodulation of PSK. Here you are receiving this PSK through antenna, that is plus minus A cos 2 pi FCT, or you can say A cos 2 pi FCT plus phi. Now this phi will change, this phi is changing either 0 or 180 degree depending upon our symbol 1 or 0 bit. So in this current detection method, we are using this separate part as compared to ASK demodulator. The square law device, we are squaring this term. After that, we are passing through the band pass filter, then frequency divider, and when we are generating the same carrier, we are multiplying with the PSK waveform here. Here we are generating the carrier from this itself PSK waveform. And then after that, when we generated the same carrier, we are multiplying with the PSK waveform by the product modulator. Then it will go pass to the low pass filter, voltage comparator, symbol 1, symbol 0 will be detected at the threshold voltage. Now what is happening here? You can see here a square cos square 2 pi FCT. Now band pass filter that will pass the certain band pass filter that will pass the certain frequency along with the carrier and stop the other frequency. Now here you can see we are using the frequency divider also. After passing through, we will get a square by 2 1 plus cos 4 pi FCT. We are expanding the formula for cos square theta, that is 1 by 2 cos 2 theta, so it will give you 4 pi FCT. Here after passing this band pass filter, we will get only this term. This will be nullified because of the low frequency component. Frequency divider, that will be divided by 2, so it will give you cos 2 pi FCT. Now here you can see we are generating the carrier after passing this 3 stages: square law device, band pass filter, frequency divider. Now this goes to product modulator and we are giving the PSK here. So here we are getting the signal, that is cos square 2 pi FCT and A, and plus minus depending upon our PSK waveform. So here you can see we are generating the same carrier through this PSK waveform. That is very important to maintain the phase difference. We have to use the synchronized phase, synchronized amplitude frequency so that perfectly match. After that, we are passing to the low pass filter. Low pass filter that will give you the plus A, minus A by 2. Now if the plus is voltage is there, minus is there. If plus is there, symbol 1 is identified, symbol 0. If minus voltage is there, we will set the VTH here. If it's less than VTH, minus will be there, symbol 0 will be identified. So here in this session, we have completed the PSK. In PSK, we have done the waveform, we have done the block diagram, we have done the bandwidth, we have done the demodulation and energy space diagram. That's it for the today's session. In the next session, we will continue the FSK, that is frequency shift key. Thank you.